this webcast continues looking at some problems that involve conservation of momentum. First, we're going to look at a collision that is completely inelastic. That means that once the two objects collide, they stick together. So the initial momentum of the system is the sum of their individual momenta, but at the end they're moving together, and so the final momentum is their combined mass times a shared common final velocity. So let's look at this first example. We have Anna and Jessica doing the cart and brick lab. That means that there's a cart that is moving horizontally, and they're going to drop a brick into that cart. So once the brick falls into the brick and the cart move together, to the right. So that's why it's a completely inelastic collision. The two masses are combined at the end. Well, we know that the initial momentum should equal the final momentum. So at the beginning, the momentum of the cart is its mass, 2.6 kilograms, multiplied by its velocity, and I'm just going to change that 28.2 centimeters per second to meters per second, so that would be 0.282 meters per second. Okay, the brick has no horizontal velocity, so the brick is not moving horizontally at the beginning, so it doesn't have any momentum at the beginning. And then that's going to equal the momentum at the end, which is their combined masses, the 2.6 kilograms for the cart plus the mass of the brick, times their final velocity, which is 15.7 centimeters per second or 0.157 meters per second. Okay, and so I am just solving for the mass of the brick. So the mass of the brick is going to be, let's see, this is 0.7332. So it's going to be that 0.7332 divided by 0.157 minus the 2.6. And so I get a mass of the brick of 2.070 kilograms. Okay. And let's do one other problem, which is a momentum plus problem. We're going to do an example here, but these types of problems, they require not only an understanding that momentum is conserved, but also an understanding of some of the other principles of mechanics. For example, maybe using kinematic equations or Newton's laws. So let's look at this first example. Tennis regulations specify that the tennis ball must bound to a height of 53 inches when it's dropped from a height of 100 inches onto a concrete slab. And we'd like to figure out what is the change of the momentum of the ball during that collision with the concrete. Okay, so just a little diagram here. We're taking a tennis ball and it's initially at a height of 100 inches. And we let it fall to strike the ground, a concrete ground, and then it bounces back up and it has to come up to at least 53 inches. So its initial position is 100 inches, and I better convert this to meters, right? I want to work in standard units. They hopefully tell me that 2.54 inches is no, I have this wrong. 1 inch is 2.54 centimeters, And I would really like to work in meters. I know that 100 centimeters is 1 meter. And so the initial height here is 2.54 meters. The final height is 53 inches. And I can convert that and I get 1.346 meters. Okay, so when the ball is falling, you know, to really answer this question, I'm looking for the change in momentum. Let me take this step back. The change in the momentum is going to be the final momentum minus the initial momentum. And so that's going to be the mass of the ball times the final velocity minus the mass of the ball times the initial velocity. Well, the initial velocity is the velocity just before it hits the concrete. So I need to find that, okay? And so I'm going to use a kinematic equation to do that. I know that as it falls, you know, the ball is dropped, so the initial velocity is 0. Its displacement is going to be negative 2.54 meters. While it's falling, its acceleration is negative 9.8 meters per second squared. I'd like to know that final velocity just before it hits the concrete. And so I'm going to use a kinematic equation. Vf squared equals Vi squared plus 2a delta x. And when I plug in all of those numbers, just before it hits the concrete, the velocity is negative 7.056 meters per second. Okay, so that is the initial velocity as it's falling. Okay, then I want to look at the ball as it is rising up again. Okay, so here what I know is that at the peak, so in this case, that's the final velocity, is going to be 0, right? At the peak of its, as it rises up, it will have slowed down to 0. The acceleration is still negative 9.8 meters per second squared. Its displacement, now this is a positive displacement, right? Because it's rising up, 1.346 meters. And now what I'd really like to know is what was that initial velocity, you know? And so here, I could actually use the same kinematic equation, Vf squared equals Vi squared plus 2a delta x, and I'm going to get that that initial velocity is 5.36 meters per second. Okay, so here, this number is what I'm looking for as my final velocity. Okay, so now I'm in a position to be able to calculate the change in momentum. It's going to be the mass of the tennis ball. Thankfully, they gave that to me in kilograms, 0.057 kilograms. The final velocity in this situation was the rising velocity, which is 5.36, but it started at an initial velocity of 7.056. That's negative. And so when I calculate this, the change in momentum is 0.695 kilogram meters per second. So it's not that these momentum plus problems are that difficult, but it's just that in addition to understanding something about the momentum, you have to remember something about Newton's laws or the kinematic equations.